Your phone shows a blue dot on a street corner, and then without warning the dot slides sideways. It snaps to a parallel road. It drifts into a river. A car's navigation voice calmly insists you have arrived even though you're still moving. On a ship, a precise track line wobbles. In a surveyor's receiver, the solution that was locked and steady turns noisy, then drops out, then comes back with a different answer. Nothing breaks in the usual sense. No screen shatters. No satellite explodes. But the one thing GPS is supposed to provide quiet, dependable certainty about position and time suddenly becomes less certain. When that happens during a solar storm, the culprit is not the satellite constellation itself most of the time. The culprit is the space between the satellite and you. That invisible corridor passes through a layer of Earth's upper atmosphere called the ionosphere, a region filled with charged particles that can bend, delay, and sometimes scramble radio signals. GPS is a radio system. Its signals are faint by the time they reach the ground, and they are exquisitely sensitive to the electrical mood of the ionosphere. In calm conditions, the ionosphere behaves in ways that can be modelled and corrected. During solar storms, it can become restless and structured, full of steep gradients and ripples, and the usual corrections no longer fit. NOAA describes this in a simple image. The ionosphere can act like a lens, bending the signal path, and when the ionosphere is disturbed, receiver models become inaccurate and errors appear. To understand why GPS can fail, it helps to picture what a GPS receiver is trying to do. Each GPS satellite carries atomic clocks and transmits a precisely timed signal. Your receiver listens to several satellites at once and measures how long each signal took to arrive. Multiply that travel time by the speed of light, and you get a pseudo-range, a distance-like measurement. With enough satellites, the receiver can solve for your position and for its own clock offset. This is already a delicate trick because the receiver is measuring time to billionths of a second, and the signals are weak and mixed with noise. Now add the ionosphere. The ionosphere delays the GPS signal, and the amount of delay depends on how many free electrons the signal passes through. In a smooth, quiet ionosphere, that delay changes slowly and predictably, with location and time, so models and correction methods do a decent job. NOAA notes that in calm conditions, single-frequency GPS can often achieve around meter-level accuracy or better, while dual-frequency systems can reach centimeter-level performance in high-precision applications. But solar storms are exactly the kind of event that makes the ionosphere stop behaving smoothly. A solar storm in the practical space weather sense is often driven by a coronal mass ejection or fast solar wind interacting with Earth's magnetic field. The magnetic connection pumps energy into Earth's high-latitude upper atmosphere. Currents intensify. Particle precipitation increases. The ionosphere heats, swells and rearranges, and one of the most important numbers for GPS total electron content, or TEC, can surge and become structured. NOAA explains that geomagnetic storms enhance the ionosphere and increase TEC, and that GPS systems cannot correctly model this dynamic enhancement, so errors get introduced into position calculations. That is the first failure mode, wrong corrections. Your receiver thinks the ionosphere is behaving normally, subtracts a typical delay, but the real delay is larger or uneven or changing rapidly. The result is a position error. NOAA gives a concrete sense of scale. During a severe space weather storm, single-frequency GPS errors can grow to tens of meters or more. The receiver might still output a position, and it may look confident, but it is confidently wrong because the model underneath is wrong. The second failure mode is more dramatic: loss of lock. This happens when the signal becomes so distorted that the receiver cannot reliably track the satellite's carrier phase or code. This can occur when the ionosphere breaks into small-scale irregularities that make the signal's amplitude and phase flicker rapidly, a phenomenon called scintillation. Think of looking at a star low on the horizon and seeing it twinkle wildly. The star is not changing, the medium is. In radio, scintillation can cause deep fades and rapid phase changes. Receivers may experience cycle slips, frequent reacquisitions, or outright dropouts. NOAA notes that when the ionosphere becomes highly disturbed, a GPS receiver may be unable to lock onto the satellite signal, and position information becomes inaccurate. A third failure mode is subtle but important timing instability. Many systems do not use GPS primarily for position, they use it for time. Cellular networks, power grid monitoring, financial timestamping, sensor networks, and countless synchronized systems depend on GPS timing. If the receiver's tracking is noisy, or if satellites are temporarily lost, or if the ionospheric delay estimate is wrong, the derived timing can jitter. Most professional systems are designed with holdover clocks and filtering, but the dependence is real. When people say GPS failed, they might mean the map dot drifted, or they might mean a timing-dependent system degraded quietly in the background. Now here is the part that surprises many people. GPS can have trouble even when there is no dramatic headline about a solar storm. There are regions of Earth where the ionosphere naturally forms instabilities every day. Near the magnetic equator, especially just after sunset, the ionosphere can develop bubbles and irregular structures that cause strong scintillation. NOAA explicitly points out that near the equator, dual-frequency GPS systems often lose lock due to ionospheric scintillation, and that these equatorial scintillations are not necessarily associated with any space weather storm. They can be part of the natural day-night cycle of the equatorial ionosphere. That means how often does it happen has two answers depending on what you mean by it. If you mean noticeable GPS degradation linked to solar storms, the frequency follows the rhythm of geomagnetic activity and the solar cycle. NOAA's space weather scales give average frequencies for geomagnetic storm levels over an 11-year solar cycle expressed as the number of days per cycle associated with each storm category. For geomagnetic storms, NOAA lists roughly minor storms, G1 as common across a cycle, moderate G2, less common strong G3, rarer severe G, 4 rarer still, and extreme G5 very rare on the order of only a handful of days per cycle. These are averages and real cycles vary with storm days clustering more around solar maximum. But the key idea is steady and practical. Mild geomagnetic storm conditions are relatively frequent, and the truly extreme conditions that can cause widespread sustained GPS disruption are rare. If you want those NOAA scale frequencies to feel more tangible, imagine an average 11-year span. NOAA's table indicates that minor geomagnetic storm days are common across the cycle. Moderate storm days occur regularly. Strong storm days occur dozens of times across the cycle. Severe storm days are rarer, and extreme storm days are rarest of all. The category that most people remember major storms that push aurora far from the poles and generate intense headlines does not happen every week. But lesser storm levels that still disturb the ionosphere, especially at high latitudes and sometimes mid-latitudes, can occur often enough to matter for systems that demand high precision. And if you mean GPS dropouts or quality loss due to ionospheric scintillation in general, then how often depends strongly on location and local time. Near the equator, scintillation after sunset can be frequent seasonally and can be strong enough to cause loss of lock even without a major storm. At high latitudes, scintillation and irregularities are often tied to geomagnetic activity and can intensify during storms. In mid-latitudes, the impact is usually milder, but major storms can push disturbed regions and TEC gradients into places that do not experience them often. So what actually happens during a solar storm from the GPS receiver's point of view? First, the ionosphere's large-scale electron content changes. The GPS signal is delayed more than usual, and that delay is not uniform. It can be higher in one direction than another, and it can shift rapidly. A receiver that relies on a standard ionospheric model begins to accumulate error. NOAA's description is straightforward. When the ionosphere is disturbed by a space weather event, models are no longer accurate, and receivers are unable to calculate an accurate position based on the satellites overhead. Second, the ionosphere becomes structured. Instead of a smooth layer, it forms fronts, gradients, and patches. If you imagine the signal travelling through a moving uneven lens, you get a sense of what happens. The receiver might still track, but it will see changing delays that look like noise. If the receiver is doing high-precision work like real-time kinematic surveying or precise point positioning, those gradients can be especially damaging because the method assumes the carrier phase is stable and the propagation path is well behaved. Third, irregularities produce scintillation. Now the signal itself starts to sparkle in amplitude and twist in phase. This is when receivers lose lock. The practical result is outages and resets, sometimes in bursts, lock, slip, reacquire. NOAA describes this inability to lock during highly disturbed conditions as one of the ways position becomes inaccurate. Fourth, in some cases, operators respond. Aviation is one area where this is treated as a real operational hazard. The US Federal Aviation Administration notes that GPS and GNSS can be impacted during solar events, causing ionospheric disturbances, and that this can degrade accuracy and impair navigational tools. That line is important because it frames the issue correctly. It is not that GPS turns off, but that accuracy and availability degrade in ways that matter for certain procedures and environments. If you listen to all of this and wonder why your phone usually seems fine even when you hear about aurora or solar storms, the answer is that consumer navigation is tolerant. A phone map is happy with 5 meters of error, sometimes even more. It also fuses GPS with other sources like cell towers, Wi-Fi positioning, inertial sensors, and map matching. High-precision systems are not so forgiving. Surveying machine control, precision agriculture, aviation augmentation, and scientific timing depend on stable carrier phase tracking and reliable corrections. Those systems are where space weather shows its teeth first. This is also why the phrase GPS can fail needs careful meaning. Many of the most common storm time effects are degradations, not total failures. The receiver may keep working, but with worse accuracy. It may work intermittently. It may work fine at one latitude and struggle at another, and it may fail in one mode like high-precision phase tracking while still providing a rough position fix. Now, the title also asks something quietly powerful: how often does it happen? And here the most honest, sleep-friendly answer is that it happens on a spectrum, and the spectrum is well described by 2 rhythms: the daily rhythm of the ionosphere and the 11-year rhythm of the Sun. On the daily rhythm, equatorial regions often experience post-sunset scintillation that can cause loss of lock independent of storms. This means GPS availability issues can be a regular nightly visitor in certain regions and seasons, even when the Sun is not throwing an obvious tantrum. On the solar cycle rhythm, geomagnetic storm days occur with frequencies that NOAA summarizes by storm category, and these categories correlate with how likely GPS performance is to degrade, especially at high latitudes and for precision applications. Minor and moderate storm conditions are not rare over the long run. They are part of the background of an active star. Strong and severe storms are less common but still recurring over a solar cycle. Extreme storms are rare. And in between those rhythms is the reality that one storm day does not guarantee GPS trouble everywhere. A geomagnetic storm can be measured globally, but its strongest ionospheric irregularities may be localized in certain latitude bands and local times. That is why someone in one place can have an uneventful evening, while someone else sees strong scintillation and receiver dropouts. If you want one more calm anchor for what often means, here is the simplest translation. Small GPS accuracy changes can occur fairly often during elevated geomagnetic activity, but the kinds of severe widespread disruptions people imagine are uncommon, and truly extreme events are rare. NOAA's scale language matches that practical view, noting that at higher storm levels satellite navigation can be degraded for hours or days, while at lower levels intermittent navigation problems may occur. One last detail makes the story feel complete. GPS is not just one frequency. Civil GPS uses multiple signals, and other GNSS systems like Galileo and GLONASS add more. Dual-frequency receivers can estimate ionospheric delay more directly by comparing delays at 2 frequencies, which helps a lot in normal and moderately disturbed conditions. NOAA notes dual-frequency systems are used to better characterize the ionosphere and remove its impact, achieving centimeter-level positioning in calm conditions. But there is a limit when the ionosphere becomes highly disturbed and scintillation dominates. Even dual-frequency receivers can lose lock. The storm does not politely respect your upgrade. It changes the medium itself. So if you ever want to picture the whole thing in one quiet image, imagine GPS as a chorus of faint, steady whispers arriving from orbit, and the ionosphere as a translucent moving curtain. Most nights the curtain is smooth enough that the whispers pass through with predictable bending. During solar storms the curtain becomes wrinkled and restless. The whispers still come, but they arrive warped, delayed, and sometimes briefly drowned in the curtain's motion. Your receiver is not failing because the satellite stopped speaking. It is failing because the air above you, electrified by the sun, stopped being a simple medium. And that is the gentle truth under the headline. GPS can fail during solar storms because space weather disturbs the ionosphere, pushing electron content and irregularities beyond what receiver models can correct, leading to larger errors and sometimes loss of lock. How often it happens depends on where you are, what fail means for your application, and where the sun is in its cycle, but the overall pattern is steady. Frequent mild disturbances, occasional strong ones, rare, extreme ones, and a daily equatorial scintillation rhythm that can mimic storm-like behavior even on quiet solar days.